Hey, my name is Manish Gupta, and in this video, I'm going to talk about a very interesting topic. Can large reasoning models actually think? Okay, so I'm sure you have heard about these large reasoning models. So unlike large language models, these models which basically output a very large reasoning trace and then basically give you the final solution, final answer. Can these large reasoning models actually think? Or they somehow just perform reasonably well, based on their pre-training knowledge or contamination in their pre-training data, compared to the test data and so on. Okay. So to be able to answer this question, the authors in this interesting paper essentially work on puzzle-based thinking problems. Four of them, Tower of Hanoi, checkers, jumping, river crossing, and blocks world problems. Their claim is that when they work on these reasoning problems, thinking problems, the point is that no pre-training knowledge can make a big difference here. There can't be a contamination in the data, in the test data compared to the training data and so on and so forth. So all of those problems get solved. Um, so what are these four problems? The Tower of Hanoi, checkers, jumping, river crossing, blocks world, they're actually very popular and famous puzzle-based thinking problems. Tower of Hanoi, very quickly, right? Here the idea is that in the initial state, so the first row denotes the initial state of all problems. The last row denotes the target state. And then there could be some middle state in the middle. Okay. So these are basically step-by-step solving problems. You start with three different pegs, and then you have to basically transfer these disks from the first peg to the last peg, right? And what you have basically, while transferring, you have to ensure that you can only move from any peg, you can only move the top disk. Obviously, a larger disk cannot be on top of a small disk ever, right? So those are the challenges. And then the point is that here there's an example shown with just three disks, but you can actually try with 10 disks as well. And with three pegs, it is all possible. It's just that the disk transfer across pegs with n disks take minimum 2 raised to n minus 1 moves. And that makes the problem more complex as n increases, as the number of disks increase. Okay. The other problem is this checkers jumping problem. So there are these blue circles and there are these, orange circles, and this is a one-dimensional array. What you want to do is to start with blue on the left, orange on the right, and you want to actually have orange on the left and the blue on the right. Okay, it's like a checkers kind of a problem. So here the constraints are that every circle can actually each of these tokens, let's call them colored tokens. So they can actually just move to an empty space next to them, or they basically can move to an empty space by hopping over max one token of the other color. Okay, so essentially now here the idea is that if you have two n checkers, basically you require at least n plus 1 square minus 1 moves to be able to solve this problem. So again, as you increase the number of tokens, the problem complexity increases. The third problem is called river crossing problem, and some of you might have heard this puzzle a lot, when solving those puzzles in various competitions and so on, right? So there's a river and there is a boat, and there are, a circle is an individual, and let's assume the triangle is basically their agent. So you might have heard variations of this problem, like the circle is a person and the triangle is a goat and so on. So basically the person is trying to cross the river with their goat. Okay. The point is that these two guys need to be together always. And here there are two pairs and they have to cross the river. So cross the river and come on the other side of the river. You see they were on the upper side and now they're on the lower side of the river. Okay. So they cross the river and we can call them as actor-agent pairs. So each of these actor-agent pairs, here only two of them are shown, but they have to cross the river and get onto the other side. And the boat has a limited capacity though. So the boat cannot carry everyone. So if there are like 10 different pairs here, 20 people can't go onto the boat at one point. Okay. Boat can actually have a capacity of max 3. Okay. So then how do you basically cross the river, ensuring that the actor-agent pairs are not separated from each other, but minimum number of minimum number of times you want to use the boat and so on and so forth, right? So that's that. Blocks world is yet another puzzle problem where basically you have multiple blocks and they're kept on top of each other and so on. And what you want to do is to start with an initial configuration and lead to the target configuration, ensuring that you always move the block from the top on any such tower in that senses and get to the target configuration. Now, these are all interesting thinking problems. Obviously, they require some sort of reasoning knowledge, mathematical understanding, algorithmic understanding. Are large reasoning models capable of generalizable algorithmic thinking to be able to solve these problems, right? So what are the experiments and what do these guys observe? So these authors actually experiment with 5 different large reasoning models: O3 mini, medium and high configurations, DeepSeek R1, DeepSeek R1 Quen 32 billion, and Claude 3.7 Sonnet thinking model. So now here are several plots that you see here. So let's talk about the top plots, these plots. So in fact, top row itself. So top row itself shows you distinction, 2 curves, each of these plots. One is for Claude 3.7 Sonnet and the other for Claude 3.7 Sonnet plus thinking. So the Sonnet model by itself is a large language model, plus thinking model is a large reasoning model. Okay. So yellow, blue, and red, these 3 different plots basically mean low complexity, medium complexity, and high complexity problems. Remember, by varying the number of actor agent pairs, or by varying the number of disks, by varying the number of tokens, and so on, you can increase the problem complexity. Okay. So these are low, medium, and high complexity problems. And then what do plots show? The plots show inference compute on the tokens, number of tokens required for the reasoning on the x-axis, and y-axis is the accuracy metric pass at k. Okay. So what do you observe from these plots? The plots basically tell you for low complexity, essentially you see that the LLM is actually better compared to the LRM. You would rather use the LLM for low complexity problems because it takes lesser compute to basically obtain a better accuracy. Okay. For medium complexity, yes, it basically turns out that the reasoning model actually gives you better accuracy compared to the large language model at all different inference compute budgets. Okay. For high complexity, what do you observe? You observe that both of the models, whether it is large language model or it is large reasoning model, both of them actually do not perform at all. I mean, they basically lead to almost zero accuracy. Okay. So in short, based on these observations, basically these guys are able to sort of divide the working of large reasoning models into 3 different regimes. The low complexity regime, where large language models are actually better than large reasoning models. And this is not true just between Claude 3.7 Sonnet and 3.7 Sonnet thinking. It's also true between DeepSeek V3 and DeepSeek R1. DeepSeek R1 is the reasoning model. DeepSeek V3 is the large language model. You observe still here that in low complexity regime, which is the yellow color, large language model is better than large reasoning model. In the medium complexity regime, you basically observe that additional thinking in the large reasoning models is helping it. Additional thinking is actually letting it actually improve on the overall results. Okay. In the high complexity regime, you observe whether it is the Sonnet models or the DeepSeek models. You observe that in high complexity regime, both large language models and large reasoning models fail. Okay. Now, let's look at the results at the bottom. So these results are for Tower of Hanoi problem, the first puzzle basically. And they basically plot the complexity in number of disks. The disks basically control the complexity, right? Versus accuracy. Okay, this plot is for versus accuracy. And you observe that, yes, I mean, the low complexity regime, the large language model, this one is basically almost the same or better compared to large reasoning model. In middle complexity regime, obviously, the reasoning model performs better. In the high complexity regime, well, both perform significantly worse. But what is interesting is this plot. This plot actually shows you complexity, but on the y-axis is reasoning effort, number of tokens actually. Okay. So in the low complexity regime, obviously both LLM and LRM perform equally, but LRM actually uses way more number of tokens. It overthinks too much. Okay. In the middle complexity regime, yes, LRM is better than LLM in terms of accuracy, but it also ends up using large number of tokens. Remember, it doesn't come for free cost, right? Basically, it uses more number of tokens. In the high complexity regime, unfortunately, basically, large reasoning model wastes more tokens than large language model, but at the same time, it doesn't really lead to any good results. It basically is leading to almost zero accuracy. Okay. But what is interesting is this, that as the complexity increases beyond 10, for example, for the Towers of Hanoi problem, somehow the large reasoning model refuses to use more tokens. Counterintuitively, it basically says that, hey, I would want to just come up with a wrong answer, and that too without increasing the number of tokens. Okay. So this is counterintuitive. It is basically, the large reasoning model is let loose. It's basically allowed to use more tokens, but doesn't use more tokens. Okay. Let's see a different perspective. So essentially, so they also analyze reasoning traces and try to understand what's going on in these reasoning traces. These are the results for all the 4 problems, right? So what is plotted here? So x-axis complexity, n equal to 1 to 3, 1 to 10, and so on. Y-axis is basically position and thinking. So what they did is that they looked at the reasoning traces for these models. For each unique intermediate solution, remember unique, first of all, intermediate solution, and then unique intermediate solution, they basically try to figure out its reasoning relative position in the entire reasoning trace, okay, percentage of the relative position in the entire reasoning trace. Correctness and specific failure move. So they also try to figure out whether this particular intermediate solution is failure or not, right? Or rather leading towards failure or not. And they can do that because these problems are all basically solvable. We have the optimal algorithm for them anyway, right? And they also have basically figured out the problem complexity, right? So for each intermediate solution, you get that, and then you plot these curves. Okay. So the tick curve basically indicates the correct solution, what leads to the correct solution finally, and the cross curve basically indicates the wrong solution at the end. Okay. So what you observe is that in the Tower of Hanoi problem, n equal to 8, after that, there is no right solution. So that's obvious. So similarly, in checker jumping, you see in the high complexity regime, there is no right solution, right? No right solution. Okay. Now, what is interesting to observe in the low complexity regime here, right, where there is n equal to 1, 2, 3, 4, let's say, right? There are a lot of correctly solved cases, right? But then for those correctly solved cases, LRMs tend to find answers early. And after that, they're just overthinking. You see, even for these, the crosses curve is actually above the ticks curve for n equal to 1 to 4, let's say, low complexity regime. So there's overthinking going on. I mean, it's inefficiently continuing to explore incorrect alternatives, even though it could figure out the right alternative, right answer right in the beginning, early in the solution. Okay. So for simpler problems, that is smaller n, the solution accuracy tends to decrease as thinking progresses. As thinking progresses, solution accuracy is decreasing, as you can see. Okay, for smaller as basically tokens get used more and more. Yeah, and that's true about many other puzzles, but more specific in Tower of Hanoi. Okay. At moderate complexity in this regime, basically, correct solutions emerge only after extensive exploration of incorrect paths. So they do explore incorrect paths, but then, finally, fortunately, LRMs are better. They can actually still give you correct solutions. In failed cases, these failed cases, what is observed is that these LRMs actually focus on early wrong answers much earlier in the sense on the y-axis, you see it's smaller values, much earlier in the reasoning trace. They actually end up with the wrong answers, and they fixate on those wrong answers, and they keep blabbering about those wrong answers only, wasting the remaining token budget. No good answers come up at all. Okay. You see, this particular plot is for Tower of Hanoi, and you see on the x-axis position in thinking, basically it's tokens, and y-axis solution accuracy. So you observe, and each of these curves is for different complexity, n equal to 1 to 3 up to 4. So n equal to 1 to 4, you basically observe that as the complexity increases, or rather, as the position in thinking increases, the solution accuracy drops. What does this mean? This means overthinking. If you think more, you basically lead to worse solutions. Okay. So this is for easier complexity tools, easier complexity problems, lower complexity problems. Okay. This plot basically just shows to you, it plots complexity and position, basically tokens. It basically just shows to you that yes, in medium complexity problems, LRMs are very nice because correct solutions emerge. I mean, this plot is actually just similar to this plot drawn at a different scale in that sense. Okay, but at high complexity regimes, basically LRMs just fail completely. So they do one more interesting experiment. I just like this experiment. So what they did is that rather than just giving the problem to the LRM, large reasoning model, they also give the algorithmic solution. They basically say, this is the way you solve the problem. Okay, this is the algorithm. This is the algorithm that you can use. And then they give an instance of the problem. Now you would expect that a model which can think should be able to use the algorithm, apply the algorithm to this problem, come up with the right answer. But what you see in these plots, the top plots are Tower of Hanoi problem. And x-axis is complexity of the problem, y-axis accuracy. The dotted curve is algorithm given curve. The default curve is the solid curve. What do you observe? Even with the dotted curve, with high complexity, the model is not able to find the solution. Now that's extremely difficult to understand. It's very surprising that these large language models, even when they're given the algorithm, they cannot execute the algorithm for the particular problem instance and come up with the right solution for high complexity problems when the complexity is higher. And that's not true just about Tower of Hanoi, it's true about checker jumping as well. High complexity, whether you give the algorithm or you don't give the algorithm as part of input, basically the large reasoning model is not able to figure it out at all. Okay. In summary, in this video, I talked about a good analysis of how large reasoning models fare compared to large language models, specifically for thinking puzzle kind of problems. The understanding can be broken down into three reasoning regimes. In the low complexity problems, LLMs are actually better than LRMs. In the medium complexity, moderate complexity problems, LRMs show advantage. They are advantageous. And at high complexity, both LLMs and LRMs actually fail. Okay. Reasoning effort sort of reduces as problems approach high complexity. And this is, again, very surprising. I mean, why would the model just refuse to think more when it is given a highly complex problem? Okay. The reasoning patterns are complexity dependent. So it basically overthinks on simpler problems. Large reasoning models overthink on simpler problems. But on high complexity problems, they just refuse to think in that sense. Okay. Even providing the solution algorithm as part of the input does not really improve performance of large reasoning models. It should be able to take the algorithmic solution, execute the instance, and give you the answer, but that doesn't happen for high complexity problems. Okay. That's it for this video. This is a very interesting paper. I mean, trying to understand what are the problems with large reasoning models. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.